Last time we were discussing about the complex eigen value problem. Complex eigenvalues, okay, complex eigenvalue problem. So, any matrix can result into the complex eigenvalues. However, certain complex eigenvalues, certain matrices have some properties which result in some interesting situation. Okay. So just like, for example, if I take this matrix A, 1, minus 3, 3, 1. In this matrix, you can see that this is a 2 by 2 matrix. And in this case, the first matrix is 1 minus 3. And the second, the first column is 1 minus 3. And the second column is 3, 1. So it is a special kind of form. For example, the general form is something like this: A, B minus B, A. And if we find the eigen values for this vector, and if these eigen values are complex eigenvalues, then we may see that if we multiply this vector by some, if we multiply this matrix by some vector, then that vector is rotated and dilated with some constant values. So this type of matrix is thus called as the rotation dilation matrix. Okay. So if this, for example, if this matrix A, AB minus BA has complex eigen values, then A is called a rotation dilation matrix. Okay, so taken as an example, if I take a vector, so let me represent a vector in this two-dimensional space. So let us say I take a vector something like this. So if this x-axis and if this is y-axis, I take a matrix U1 as represented by this coordinate 1, 0. So matrix U1 can be represented by this, vector U1 can be represented like this, 1, 0. Okay, so if I take A times U1, so 1, 3, minus 3, 1, and then I take it as 1, 0. So then I will get 1 times 1, and then 3 times 0 is 0, minus 3, and minus 3 times 1 is minus 3, and then 0. So I will get 1 minus 3. Okay, I will get 1, 0, and then I get 1 minus 3. If, for example, I take another vector, so for example, vector U2, so which can be represented as 0, 1, U2, 0, 1, and I multiply A by U2, so 1, 3, minus 3, 1, and then it is 0, 1, so it will be 1 times 0 is 0, and 3 times 0 is 1, so it will be 3. So it will be 3, 1 times 0 is 0, 3 times 1 is 1, and then minus 3 times 0 is 0, then 1. So it will be 3, 1. So if we compare this 1, 0 matrix, so this one from 1, 0 to the transformed matrix 1, minus 3, and then from this original matrix 0, 1 to this transformed matrix 3, 1. So we can see some relationship. So first of all, the relationship is that let's find its the modulus of this matrix, okay, or the length of this matrix, sorry, this vector. So the length of this matrix, for example, is U1 is 1 square plus 0. So 1 square plus 0, it is 1. Okay, and then the transformed matrix is, the length is, that is the length of this AU1 will be equal to 1 square plus 3 square. So it is then under root 10, square root of 10. So the lengths change from 1 to square root of 10. Okay, so for this U1, that is the length of U1, sorry, U2. The length of U2 is under root 1, so 1. And then AU2 is also square root of 10. So this means that there is this constant change in the length. So this means that it is the change in length, okay, change in length as a constant ratio, okay, has happened. So it means that we will see that, so for this we will see that the matrix, that is the vector, has dilated, okay. So for the change in length, we use the term dilation, okay. So we will say that we say this type of thing as the vector dilation, okay, vector dilation. And the other thing was that the rotation. So for the rotation, we see the angle. So for example, the vector has changed from 1, 0 to 1, minus 3. So it will be 1, and then minus 3 will be here, right? The vector has changed into this direction. And for this one, it has changed from 0, 1 to 3, 1. So 0, 1 to 3, 1. So 3, 1 will be 1, 2, 3, and then 1 will be here. So it has changed to like this. And also there is some rotation which has taken place. So it is the same rotation which was before, and after that it was also the same rotation, okay. So by the same amount of rotation, and that same amount of rotation is equal to the tangent inverse of 1 over 3, okay, tangent inverse of 1 over 3. So therefore in this case it will be minus 3 times, yeah, so 1 over 3. So same amount of rotation. So rotation and dilation are some of the properties of these kinds of matrices. So in this way, then we can find the rotation, okay. So therefore, as a formula, if we can, if we say, if we have been asked that find the rotation and dilation, okay, find the rotation and dilation of if this matrix A 1 minus 3 3 1. So our first step will be find the eigenvalues. Okay, find the eigenvalues. And remember that the matrix A should be in this form, A B minus BA, or something like this. So the form of A should be A, B minus B, A. Okay. And it should be a 2 by 2 matrix. We are only talking about 2 by 2 matrix for such a property. So find the eigenvalues. So for example, for this we will need to find the eigenvalue. So it will be 1 minus lambda for the characteristic equation, minus 3, 3, 1 minus lambda, and they take the determinant equal to 0. So it will be 1 minus lambda square minus 3 times minus 3 is equal to 0. So it will be 1 minus lambda square plus 9 is equal to 0, or 1 minus lambda square is same as the lambda minus 1 square is equal to minus 9. And if we take the square root of that, so lambda minus 1 is equal to minus 3i. So it will be, because minus 9 square root is 3i, okay, and then it will be, by taking the square root, it should be plus minus 3i. So it will be, so lambda 1 will be equal to, you can take lambda 1 is equal to 1, minus 1 goes to on the other side, 1 minus 3i, or lambda 2 will be equal to 1 plus 3i. Okay, so this will be the these will be the eigenvalues. So we can take any of these eigenvalues, and then we can find the rotation. Okay, so the rotation is equal to the tangent inverse B over A. Okay, so what is B and A? So B and A is are the components of the complex eigenvalue. Okay, so if the eigenvalue lambda is equal to A plus minus BI, so then B will be the imaginary part, and then coefficient of the imaginary part, and then A will be the real part. So it will be tangent inverse B over A. So tangent inverse 3 over 1. So B in this case is, we have taken as minus 3. So it will be minus tangent inverse 3. So in radian terms, it will be about minus 1.24 radian if you will calculate by the calculator. Or on the other hand, if you take lambda 2 is equal to 1 plus 3i, so you will get 1 plus 1.24 radian also, which is also correct. And the dilation is actually the length of this number vector, which is represented by this complex number. So it will be A square plus B square. So it will be 1 square plus 3 square. It will be under root of 10. Under root of 10. Square root of 10. So is it clear?
Yes.
Yeah, so this is how you find the rotation and dilation of a matrix of a specific form. Okay, 1 minus 3 3 1. Okay, remember that we don't find the rotation and dilation of any 2 by 2 matrix. So this matrix should be of this form. Okay, the matrix should be of this form. Okay, so now the question is, okay, we have this rotation and dilation, and then we also see that there are some properties of the vectors associated with the rotation dilation matrix, which we have seen previously that the vectors are rotated and increased or decreased in length by specified amount. So which is okay, which is fine. So, but do we have any specific application of this thing? So the answer is yes, we have some application as well. And the application is this. So application of uh, rotation dilation matrix is that we can factorize we can factorize 2 by 2 matrices with complex eigenvalues. Okay, so we can factorize 2 by 2 matrices with complex eigenvalues. Okay, remember that this matrix should be of 2 by 2. Okay, it can be any 2 by 2 matrix, but the condition is that that matrix should have complex eigenvalues. So only then we can factorize it, and we can factorize in it what form. So suppose if that matrix is A, we can factorize it into like this: P, B, P inverse. Okay, P, B, P inverse. So it has an analogy with the diagonalization process. So what was the diagonalization process? Diagonalization A, P, D, P inverse. However, in that process, the matrix A was for any square order, 3 by 3, 4 by 4, like that. And not every matrix can be diagonalized. Same also is over here. Not every matrix can be factorized in this process. And the other difference is that here we had the diagonal matrix, which consists of the real eigenvalues, okay, real eigenvalues. Here we are only talking about the 2 by 2 matrix with the complex eigenvalues. Okay, so here B will be a B will not be a diagonal matrix. Okay, B will be the hidden. Okay, hidden rotation dilation matrix. And remember that hidden rotation diagonal matrix is of this form: A, B minus B, A. Okay, so we will have some matrix A, which is not not necessarily in this form. I mean, you can take any matrix which is not in this form, but we can factorize that matrix into into this form. Okay, in which the B will be the rotation diagonal matrix AB minus BA. And what will be the P? P will be just like in this case, in the APDP inverse, P will be the matrix formed from the eigenvectors, okay? Formed from the eigenvectors of this case. So therefore, we are now talking about the A, P, B, P inverse factorization. Okay, so let's see it with the help of the example. Suppose if we have matrix A and then we want to factorize into PBP inverse. So in fact, suppose if we have matrix A as 3, minus 2, 1, 1. Okay, so this matrix is not in this form. So this is not a rotation dilation matrix. So rotation dilation matrix will be like something like this. So 1, 1, 1, minus 1, 1. Okay, so this is a rotation dilation matrix. Okay, maybe 1, minus 3, 3, 1. So this is a rotation dilation matrix. Okay, so I mean, there will be some rotation dilation matrix which will be a which will be associated with this, and then we can write it like P inverse. Okay, so we need to find it. So how we are going to find it? So that rotation dilation matrix will be based on the eigenvalues. And remember that this matrix should have the complex eigenvalues. So if matrix does not have any complex eigenvalues, then we cannot factorize it like this. Then in that case, we will try to factorize it with this approach. Okay. Okay. So now A is 3, 1, minus 2, 1. So let's find its eigenvalues first. So it should be 3 minus lambda, 1 minus 2, 1 minus lambda. So this is the determinant, and then from here we write the characteristic equation. So 3 minus lambda, 1 minus lambda, minus 1 times minus 2 is equal to 0. So what we get is 3 times 1 is 3. 3 times lambda is minus 3 lambda. Minus lambda times 1 is minus lambda. Minus lambda times lambda is plus lambda square. Plus 4 is equal to 0. So what we get is lambda square minus 4 lambda. Okay. Lambda square minus 4 lambda, and then what we have is plus 4, and then we have plus 3 is equal to 0. Okay, so what we get is,
actually it's not 4 in the second row, it's 2. 3 plus 2.
It is, yeah, maybe I make a mistake. Let me check again. So it is 3 minus lambda, 3, 1, minus 2, 1, 3, 1, 3 minus lambda, 1 minus 2. Okay, 3 minus lambda into 1 minus lambda into minus 1 into minus 2. And then it should, it is, so it is 3 minus 3 lambda minus lambda plus lambda square, and then it should be plus 2. Yeah. So it should be plus 2. So what we get is, so lambda square minus 4 lambda, okay, lambda square minus 4 lambda plus 5. So if I want to complete these square, so what I can do is lambda square minus 4 lambda plus 5. Okay, so it is like this. And then we can solve it by the quadratic formula. So plus 4 plus minus 4 square is 16, minus 4 times 5 is 20, divided by 2 into 1, 2, that is 2. So it will be 4 plus minus 16 minus 4 is minus 4, minus 4 square root is 2i, okay, over 2. So what we get is lambda is equal to 2 plus minus I. Okay, so we get lambda is equal to 2 plus minus I. So we can take any value of the lambda, say for example, lambda 1 we take as 2 minus I. Okay, you can even take 2 plus I as well. It doesn't matter. So from here now we can try to find the eigenvectors. So the same process as we before. So we will take this as 3 minus 2 plus I. Okay, and then 1, and then minus 2, and then I will take that is 1. Okay, 1 minus 2 plus I. So, and then it's augmented matrix. So from here, what I will get is 3 minus 2, 1 plus I, and then I will get 1, and then minus 2, and then I get is minus 1 plus I, and then 0, 0. So we want to perform the row echelon operations. So what we can do is over here, I can divide this first row by 1 plus I. Okay. So what I can do is I can divide this first row by 1 plus I. So it will be 1, and then 1 over 1 plus I, and then it will be minus 2, and then minus 1 plus I. That is 0, 0. Okay, so to make this as 0, so what I do is 1, and then this one I can simplify. So for example, 1 over 1 plus I can simplify like this. 1, I can multiply it 1 minus I over 1 minus I. So it will be 1 minus I. Okay, 1 minus I, and then this is 1 square, that is 1, and minus I square, which is minus 1. So minus minus, that is plus 1, plus 1. Okay. So it will be 1 by 2, 1 minus I. Okay. So it will be 1 by 2, 1 minus I, and then that is 0. So what I do now over here is I multiply this first row by 2, okay, and then add it to. So that will make it 0. And now multiply by 2, so it will be 1 minus I, and it is minus 1 plus I. So 1 minus I, and then plus minus 1, minus 1 plus I. So 1 cancels with 1, I cancels with I, so it will be 0. Yeah, so this is correct. So now what I get is 1, and then 1, and then 1 minus I by 2, and then 0, 0, 0, 0. Okay, maybe I can write it in the next column. So what I get is, again, I get 1 minus I over 2, 0, 0, 0, 0. So from here, for example, one of the row is 0. So maybe if my matrix is U1, which is equal to K1, K2, so I can take K2 as equal to S. Okay, so K2 is equal to S. So therefore, K1 plus 1 minus I over 2 S is equal to 0. So K1 will be equal to minus 1 plus I over 2 S. So therefore, U1 will be equal to minus 1 plus I over 2S over S. So it will be, if we multiply by, if I multiply it by 2, so then what I will get is, I can take S constant and multiply by 2, so it will be minus 1 plus I, 1. Okay. minus 1 plus I1. And this I can write like this as well. So it can be written like this. For example, I divide them into the real and the imaginary part. So it is S. So real part is minus 1, 1, and then plus I. So the imaginary part is 1, 0. Okay. So it is minus 1, 1, and then 1, 0. Okay.
У меня одного лагает?
Нет, у всех.
Hello.
Oh.
Yeah, I don't know what happened, but I was suddenly disconnected, and now I have been connected again. But that screen has been, oh, I have lost that screen. Okay. I think I hope that it may be recorded. Recording maybe is not stopped, but I have lost that screen actually. This.
When we multiply the first element by 2, we also should multiply it by second element by 2, yes?
Yeah, I was just trying to do it and then suddenly, but anyway, we have how much time left? Okay, let's do it again. Okay, so this time I will do it quickly. Okay. So what we were doing is last time, because I have lost everything in front of me. So A was this. A was 3, 1 minus 2, 1. 3, 1 minus 2, 1. Okay. And we find its eigenvalue was 2 plus minus I. Okay. And from here we can find its eigenvector. Okay. So for example, the eigenvector is, if we take 2 minus I, so then 3 minus 2 is 1, and then 1, and then minus 2, and then 1 minus 2 is minus 1, and then this will be plus I, and then this will be plus I. Okay, so if I take 0, 0, these matrices, so what we get over here is 1 divided by 1 plus I, 0, and then minus 2 minus 1 plus I, and 0. And then I multiply this, so 1 plus I, so that was 0, because we multiply by 2, then it will be 0. And then if I multiply by 2 by this, so for example, it will be 2 over 1 plus I, and then it is minus 1 plus I. So if I solve it, so it will be 1 plus I, that is 2, and then that is, we are going to multiply it. So it will be 1 into, it will be minus 1 plus I, and then it is minus I, and then I square, that is minus square, minus 1. So I cancels with I, and then 2 cancels with 2 minus 1. So that will be 2. That will be 0. Okay. So 0, 0 as before. So from here we get is x1. So takes just like x1 plus x2 times 1 over 1 plus I is equal to 0. So x1 is equal to minus x2 over 1 plus I. Okay, and what we get now over here is the solution u1 is x1 is equal to minus x2 over 1 plus I, and then that is x2. Okay, so minus x2 I take as common, so it is 1 over 1 plus I, and then it will be minus 1. Okay, so maybe we can simplify it. Okay, 1 over 1 plus I is into 1 minus I over 1 minus I, so it is 1 minus I over 1 plus 1, that is 2. Okay, so it is actually x2 into, this is 1 minus I over 2, and then that is equal to, that is minus 1. Okay, and now we have multiply by 2, so it will be so it will be x2 or whatever you have, 1 minus I over minus 2. Okay, and so therefore u1 we will get like 1 minus 2, and then it will be I, and it will be minus 1, 0. Okay, so therefore we will get a matrix P over here, that will be equal to 1 minus 1, 0, sorry, 1 minus 2, and 1 minus 2, minus 1, 0. Okay, and then this can be then its inverse can be found, and then it can be you can say that A is equal to P B P inverse. Okay, so if I have not made any mistake in the calculation, then I think our answer may be correct. So okay, so it will be, yes, we started from 3 1 minus 2 1, and its eigenvalue was lambda is equal to 2 plus minus I. So we take lambda is equal to 2 minus I, and then 3 minus 2 is 1. 3 minus 2 is 1. Yeah, 3 minus 2 is 1, and then that will be plus I. And then this is 1, and then this is minus 2, and then 1 minus 2 is minus 1. Minus 1 plus I. Okay, so I divide it by 1 plus I, so it will be 1 over 1 plus I, then 0 over 1 plus I. Okay, and then it is minus 2 into minus 1 plus I is 0. Okay, and then it is 1 over 1 plus I, and then when I transformed it, so it was 0. So the first term which I get is x1 plus x2 into 1 plus I is equal to 0. So x1 is equal to minus x2 over 1 plus I. Okay, so in this case, the vector u can be written as the vector u can be written as this one. Yeah, the vector u can be written as minus x2 over n plus I, and then it is x2. Okay, and then I took minus x2 as outside, so it is 1 over 1 plus I, and then it is plus 1. Okay, it is -1. And then x2 is equal to, because 1 over 1 plus I can be written as 1, if you multi-rationalize it, 1 minus I over 1 minus I. So it is 1 minus I, 1 square plus 2 is 2. So 1 minus I over 2, it is -1. So it is 1 minus, if we multiply by 2, 1 minus I over -2. So correct. So I think in this case, then you can write like in this form, okay, P, and then after from P, then you can find the P inverse as well. And the matrix B will be written as matrix B is A, B minus B, A. So what is A? A is 2 and B is 1. Okay, 2, 1, and then minus B, that is -1, and then 2. So matrix B will be this. And from P, we can find the P inverse by the quick method. So in this way, then we can find the, you can factorize this matrix A into P, B, P inverse. Okay, so that is all for this question. Okay, so do you have any questions about this?